Hey there, and welcome to Raylene Math. In this video on the dot product, we will consider what does it mean to multiply a vector by another vector. So far, we've seen a vector that's been scaled or multiplied by a scalar. Vectors are not scalars because they have more than one component. They represent a magnitude and a direction, whereas a scalar is just a magnitude or a how much. So if I were to take this vector and to scale it by a number 2, I would actually be changing the size of it to be twice as big. But I wouldn't be changing the direction of the resulting vector. And so this vector here is the first vector scaled by 2, or multiplied by the scalar of 2. What we really want to know is what does it mean to multiply a vector by a non-scalar, another vector. And so there are two types of vector products. One is known as the vector product A cross B, and sometimes it's just called the cross product, and the other is called the scalar product, but it's still when two vectors are joined by multiplication, but this time it's called the dot product. This is the one that we're looking at now. So the first way we're going to define the dot product is using the polar components, the magnitude and the direction. And the dot product is formed by taking the magnitude of each vector and multiplying it by the cosine of the angle between the vectors. We'll see a geometric interpretation of this in a later video. First, let's remind ourselves what the I hat vector is. The magnitude of the I hat vector is 1, and the direction is 0 degrees. And if we sketch it, it looks something like that. Meanwhile, the j hat vector is also a unit vector, as we can see by the hat notation for the vector. It has a magnitude of 1 and is pointing in the angle or the direction of 90 degrees. Recall that a linear combination of just these two parent vectors can create any vector in the two-dimensional plane. For example, 3i hat minus 4j hat is a new vector which is found by taking 3 I hats to the right and 4 j hats down. And the resultant vector is if we had gone from the initial point to the final point directly without bypassing through the second point. And so the black vector is the vector 3i hat minus 4j hat. Anyway, on to the dot product of these vectors. If I want to find the dot product of I with I, the definition for the polar form is to take the magnitude of the first vector, which is length 1, or magnitude 1, multiplied by the magnitude of the second, and multiplied by the cosine of the angle between. Well, if I have another j hat or I hat vector here, I see that they are in the exact same direction, and if two vectors are in the same direction, then the angle between them is 0. And so the angle between these I can find by subtracting 0 degrees from one minus 0 degrees from the other. And I get 1 times the cosine of 0 is 1. Similarly, in part B, to get j hat dot j hat, we take the magnitude of the first times the magnitude of the second times the cosine of the angle between the vectors. And it's the same vector, so it's the same angle between, same direction for each one, which means the angle between them is 0. And so 1 times the cosine of 0 degrees is equal to 1. In part C, we have I hat dot j hat. So we take the magnitude of the first vector times the magnitude of the second vector. Now you'll notice I'm calling this a dot between the two vectors, but between two scalars I'm calling it times. And so that will be the indication that we're dealing with scalar multiplication, regular old multiplication of real values, versus multiplication of two vectors, which will produce a scalar quantity. And then we have multiplied by the cosine of the angle between the two vectors, and if we're starting from vector I hat to j hat, then the angle between them can be designated by going from I hat to j hat is a positive angle, and so this is going to be 90 degrees for the j hat minus 0 degrees for the I hat. We get 1 times the cosine of 90 degrees then is equal to 0. In part D, we have the reverse, j hat dot I hat, which is the magnitude of the first times the magnitude of the second times the cosine this time of 0 degrees minus 90 degrees, which is 1 times the cosine of negative 90 degrees. Cosine has even symmetry, so the cosine of negative 90 degrees is the same as the cosine of 90 degrees. Either way, we get an answer of 0. Part B is giving us two rectangular forms of vectors A and B, and then showing that the dot product A dot B is given by this rectangular notation, ax bx plus ay by. Essentially what we're going to use is the polar form to work out the rectangular form of the dot product. When we come up with the dot product for two vectors, we can use regular multiplication rules of distribution, and so we're going to expand this with distribution of the first vector over the second vector. And it looks like this. The first will be distributed across, and we get ax I hat dotted with bx I hat, and then I'm going to take the ax I hat and distribute it to the second term, which gives us plus ax I hat dotted with by j hat. And I'm going to repeat the same thing with the second term of the first vector. So it's really nice using the standard vector notation here because we can borrow from our prior knowledge of the regular algebra rules of distribution. The next term we get is ay j hat dotted with bx I hat, and then we have ay j hat dotted with by j hat. We get to use some rearrangement, some associative and commutative properties here. We can take the two scalars, ax, bx, and multiply them together as a coefficient of the dot product of I dot I. Now we worked out I dot I as well as all of the other three dot products in the previous example. So once we have it rearranged, we can take that information and simplify the result. So we go all the way across. We get four different terms, and from these four terms we make some substitutions. We recall that I dot I is equal to 1, as well as j dot j equal to 1. However, I hat dot j hat is equal to 0, and j hat dot I hat is equal to 0. So that leaves us with only two terms remaining, and those terms do not involve I hat or j hat at all. And so we end up with this rectangular form for the dot product from the polar form that we had. So we've shown what we wanted to. Had we started off with a proper proof format, we could have said that the left side is equal to this, which is equal to the right side. And then we could write QED for Latin for it was shown, or it was demonstrated. Now to summarize, we have two vectors that could be either given in polar form or in rectangular form. And when we are looking for the dot product, we can either look for it in the polar or the rectangular form. And a few notation things to recall is that this notation with the double, looks like double modulus of a vector is the magnitude, and we sometimes write it just with a and no vector bar over top. Same thing for the b. We are going to define theta to be the angle from vector A to vector B, so it's the final angle minus the initial angle, and that value will never be more or outside the interval of negative pi to pi. And we also have the x and the y components, or the horizontal and vertical components of the vectors. We could see if we have a vector A here in blue with an angle alpha, and we have, let's say, a red vector here of B with an angle in standard position of beta, that the angle in between them here is theta, or beta minus alpha. If we are going to do the dot product from A to B, then we measure from A to B, which gives us the angle beta minus alpha. However, if we reverse the direction, we would be measuring the angle from B to A, and we would get an angle of alpha minus beta. However, the cosine of beta minus alpha is the same as the cosine of alpha minus beta because of even symmetry. And so it's not really going to matter as far as the dot product is concerned whether we measure from one vector to the other or the reverse. So we have here the polar form of the dot product, magnitude of the first times magnitude of the second times cosine of the angle between them. And we have the rectangular form of the dot product, which says the product of the two horizontal components added to the product of the two vertical components. What we see then is that we have the dot product is expressed in polar form or rectangular form. These two expressions are equal to each other, and very often people like to isolate this cosine theta and imagine that they have a third new result. I like not really to write that as a separate formula, but just to keep in mind that the dot product A dot B has some unknowns, a magnitude of one, a magnitude of the other, an angle in between, and the horizontal and vertical components. So depending on what I am given in a problem or what I'm asked to solve for, I could use any combination of two sides of this to make an equation to solve for what's missing. In this exercise, we will work out the dot product of two vectors in both rectangular and polar forms. We have the vectors A and B in rectangular forms, so we'll do that first. We take the product of the horizontal components and add it to the product of the vertical components. So we have 1 and then negative square root of 3 for the horizontal and vertical components of A, and likewise we have negative 4 and 4 for the horizontal and vertical components of B. And so when we multiply through, we get negative 4 minus 4 times the square root of 3, which is a scalar result, and it does not have any I hat or j hat. For part B, we want to use the polar form, but we first need to come up with the vectors in polar form. So I'm going to sketch my vector A and my vector B so that I can see the magnitude and the directions by forming right triangles. I'm going to start my vectors in standard position, which means that they begin at the origin. And then the instructions for vector A say to move one space to the right and the square root of 3 spaces down. That forms a right triangle in quadrant 4, and we have a base and a height with direction of negative square root of 3, and this actually is a very familiar triangle with special angles. It has a special reference angle of pi by 3, and so I can see that my actual angle for vector A is going to be 2 pi minus pi by 3, or specifically it's going to be 5 pi by 3. Furthermore, if I want to come up with the magnitude of the vector, I can use magnitude of vector A, call it just A, and I can use the Pythagorean theorem. And so I'm going to get positive 1 squared plus negative square root of 3 squared, which is equal to 1 plus 3 is 4, and the square root of 4 is 2. And that should ring a bell because if I have this triangle, 1 square root of 3 and 2 is the basic triangle with a reference angle of pi by 3. And so now I know that the magnitude of vector A is 2 and the direction is 5 pi by 3. I'm going to repeat the process for vector B. Well, it turns out that I have another special angle here. I have an isosceles triangle in quadrant 2, and so my angle for B, so I'm actually going to use a subscript here to indicate that this is a special angle theta. I could have called it alpha as well. I could also call this angle beta. It's going to be pi minus the reference angle of pi by 4, which is 3 pi by 4. And by using Pythagorean theorem, I can get the magnitude of vector B to be negative 4 squared plus 4 squared under the square root, which is going to be 4 times the square root of 2. Again, if I know that I have a special triangle with equal sides here and here, maybe I call this 1, 1, and the square root of 2. I'm basically taking a scale factor of 4 to get a triangle with base and height of 4, and therefore I can scale my hypotenuse accordingly to get 4 times the square root of 2 to be the hypotenuse, or the magnitude. So now we're going to use the dot product in polar form to come up with the dot product of A and B. The dot product in polar form says to take the magnitude of the first, multiply by the magnitude of the second, and multiply by the cosine of the angle in between. Now the way I've written this, I have A dot B, which means I would take angle B minus angle A. But because of the even symmetry of cosine, it doesn't really matter which direction we measure the angle in. I am going to write my vector B somewhere where I can find it. My vector B has a magnitude of 4 square root 2, and it has an angle of 3 pi by 4. Since it doesn't matter which direction I subtract, I find it easier to subtract so that I get a positive difference between the angles, and I work out 5 pi by 3 minus 3 pi by 4. So subtracting the two angles gave a difference of 11 pi by 12, which is not a special angle that I know how to evaluate directly. However, I do get 8 times the square root of 2 times the cosine of 11 pi by 12. Now this had better be a negative answer because I got a negative answer in part A. If I factor out a negative, it'll be negative times 4 plus 4 root 3. I can use some trig identities to work this out, and I'll pause the video and just work out a few lines of that so you can compare it for yourself. So it turns out if we go back to the dot product in polar form, the magnitude of the first times the magnitude of the second times the cosine of the angle between the two, it's a good place to start because we can use our cosine identity to expand the cosine of one angle minus another. The expansion looks like this, and then substituting or evaluating each of the individual trig ratios, we see that we can do some reducing. We've got a denominator of 4 in each fraction, and that 4 can divide here, leaving us with a 2. So we have 2 square root 2 outside, and then the first numerator or term is going to be negative square root of 2, and then we have minus the square root of 6. I'm going to leave it as negative square root of 2 times square root of 3, however, because then I'm going to factor out the square root of 2 to multiply by this square root of 2. When I factor it out, the square root of 2 that factors out multiplies by the existing square root of 2 to give 2 times 2, and then we have negative 1 minus the square root of 3, which is equal to negative 4 minus 4 square root of 3 that we saw in part A. So it's good that we get the same result, and you can decide for yourself which method is easier. That's the dot product using the polar form and the rectangular form.